Hi, welcome to Medical Tests, Bayes Theorem, and how a first guess can lead to an absurdity. This video will present a brain teaser in probability that will demonstrate Bayes' theorem. It will be somewhat like that shown in the video Bayesian Logic at the Vet, a brain teaser, but you don't need that video to understand what's going on here. The problem that we'll show here is one that a lot of people would get wrong the first or second or third time that they see it. We'll show how to get the right answer and how it relates to Bayes' theorem. But in this video, we'll also show how the answer that most people would initially guess must be wrong, as it leads to an absurdity. Now, you'll probably get more out of this video if you know a little about Bayes' theorem. If Bayes' theorem is new to you, you might want to check out the video Introduction to Bayes' Theorem, or some of the other videos on Bayes' theorem available on this channel. Okay, let's get started. So let's say you go to your doctor and they test you for some disease. This disease pops up randomly in 1 in 10,000 people, and there is no reason to think that you are more or less likely than average to have the disease. The medical test has a false positive rate of 0.1% and a false negative rate of 0.1%. This means that of people who take the test but do not have the disease, 99.9% of them get a correct negative result, and 0.1% of them get an incorrect positive test result. Similarly, of people who take the test and do have the disease, 99.9% get a correct positive result, and 0.1% get an incorrect negative result. So, your test comes back positive. What is the probability that you have the disease? If you'd like to take some time to try to figure out the answer, you can pause the video now. Oh, and by the way, the answer is not 99.9%. Okay. Now let's get the solution. Your test came back positive. What we really want to know is, given that you tested positive, what is the probability that you have the disease? Another way of asking this is, of people who test positive, what fraction of them actually have the disease? Now, there are 2 ways one can test positive for the disease. A person can have the disease and get a correct test result. Or they can not have the disease but get an incorrect test result. Let's look at both of these possibilities. First, let's look at people who have the disease and get a correct test result. So 1 in 10,000 people has the disease. So the fraction of people who have the disease is 0.0001 or 0.01%. Of these, 99.9% get a correct positive test result. So, of people who have the test, the fraction who truly have the disease and who receive a correct positive result is given by 0.0001 times 0.999, which equals 0.0000999, or 0.00999%. Now, let's look at people who do not have the disease but get an incorrect test result. Of people who take the test, 9,999 out of 10,000 do not have the disease. So the fraction which do not have the disease is 0.9999, or 99.99%. Now, 0.1% of these will get an incorrect positive test result. So, of people who have the test, the fraction who don't have the disease, but who get an incorrect positive test result, is 0.9999 times 0.001, which equals 0.0009999, or 0.09999%. Okay, so what we've seen so far is the following. The fraction of people who 1. Have the disease and 2. Get a correct positive test result is 0.0001 times 0.999, which equals 0.00999%. And the fraction of people who 1. Do not have the disease, but 2. Get an incorrect positive test result is 0.9999 times 0.001, which equals 0.09999%. So of those people who test positive, the fraction who actually have the disease is given by the number who have the disease and test positive divided by the number who test positive. And that equals the number who have the disease and test positive divided by the number who have the disease and test positive plus the number who don't have the disease and test positive. Now, putting in the numbers that we just got, we get that this is equal to 9.1%. So in this case, even though you tested positive, there is still only about a 9% chance that you have the disease. We can also show this with Bayes' theorem, which says that the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. So here we can set A equal to has disease and B equal to tests positive. So then Bayes' theorem tells us the probability that a person has the disease, given that the person tests positive, is equal to the probability that the person tests positive, given that they have the disease, times the probability that the person has the disease divided by the probability that the person tests positive. Now, the probability that the person has the disease is the rate of the disease in the general population, 1 in 10,000 or 0.0001. The probability that the person tests positive, given that they have the disease, is the probability of a person with the disease getting a correct test result. That was 99.9% or 0.999. And the probability that a person tests positive is the probability of getting a positive result, evaluated including both people who have the disease and people who don't. We saw that this was 0.00999% plus 0.09999%, which equals 0.10998% or 0.0010998. So, using those numbers, we get from our Bayes' theorem equation that the probability that a person has the disease, given that they test positive, is equal to 0.999 times 0.0001 divided by 0.0010998, and again, that's approximately 9.1%. So it's good to see that we got the same result, 9.1%, with both methods. However, this result is very non-intuitive. Most people, when told that the test yields a correct result 99.9% of the time, guess that if you get a positive result, the probability that you have the disease is 99.9%. Let's look at this a few ways to try to make some sense of it. Okay, so first, this disease is pretty rare. In particular, before you take the test, the probability that the test will be wrong is 10 times as large as the probability that you have the disease. So compared to the disease itself, an incorrect test result isn't rare at all. So the positive test results can be dominated by people who don't have the disease but who get an incorrect result, instead of being dominated by people who have the disease and who get correct results. But you might be wondering, if the positive test results can be dominated by people who do not have the disease but who receive incorrect results, how can the test still be 99.9% accurate? So the test does give the correct result 99.9% of the time. And also, it gives the correct result for 99.9% of people who have the disease and for 99.9% of people who do not have the disease. But this does not mean that it gives the correct result for 99.9% of people who receive a positive result, or for 99.9% of people who receive a negative result. Because so few people have the disease, the vast majority of the time that the test gives an incorrect result, it is reporting a positive result for a person who does not actually have the disease. To show this more explicitly, we could imagine a population where nobody has the disease. In this case, 100% of the time that the test gives an incorrect result, it gives a false positive. But this is not because the test is biased to give false positives instead of false negatives. It is because if there are no people with the disease, it is not possible to give a false negative. All the negatives are correct, and all the positives are incorrect. Now, we should point out here that in our situation where the false positive rate is much higher than the rate of the disease in the population, the test does not really provide very much information. Now, this could change if there was some reason to believe that your chances of having the disease were higher than those of the general population. For example, if you had symptoms consistent with the disease, then having this test would make more sense. In fact, let's note that if only 1 in 10,000 people has the disease, a fake test that always gives a negative result would be correct 99.99% of the time, better than the hypothetical test we're considering here. Now, this test would give an incorrect result to every person who has the disease and a correct result to every person who does not have the disease. Of course, despite its accuracy rate, such a fake test has no diagnostic utility whatsoever. Now, it can still be hard to shake the idea that if a test for a disease is 99.9% accurate, and you get a positive result, that the probability that you have the disease is 99.9%. So let's look at one more point. let's show that the logic which leads to the belief that the probability of having the disease is 99.9% leads to an absurdity. So let's imagine that it was true that if a test is 99.9% accurate and it gives you a positive result, there is a 99.9% probability that you have the disease. It stands to reason that if the test was instead 90% accurate, your probability of having the disease would be 90%. And to push the idea further, if the accuracy was 50%, your probability of having the disease would be 50%. So let's again take the rate of the disease in the population to be 1 in 10,000. Your doctor offers you a test that has a false positive rate of 50% and a false negative rate of 50%. The test will cost $120. You decide to take the test. So the doctor pulls out a coin, flips it in the air, and it comes up heads. The doctor says, "It came up heads. You've tested positive." Do you still believe that your probability of having the disease is 50%? Of course, a coin flip has no diagnostic utility whatsoever. Your probability of having the disease must still be 1 in 10,000. But a coin flip does have a false positive rate of 50% and a false negative rate of 50%. So we can see in this case that the accuracy of the test is not the same as the probability that you have received a correct result. Okay, so let's summarize. Here we've seen that we can get some non-intuitive results in probability. We've looked at an example of a test for a disease with non-zero false positive and false negative rates. We calculated the probability that you have the disease given a positive test result. We first did this from first principles, and then we used Bayes' theorem, getting the same result. We also saw that most people's initial guess leads to an absurd result if used in the case where the test's accuracy is poor. Nonetheless, the results we've seen here might still be somewhat surprising. If you'd like to see a similar example presented from a somewhat different perspective, you might want to check out the video Bayesian Logic at the Vet, a brain teaser.